In this lecture, we want to discuss computational complexity. This is sometimes referred to as runtime complexity or asymptotic complexity, or just as simply complexity. However, all of these terms refer to the same thing. Computational complexity is a way to characterize the performance of computer algorithms. Specifically, we want to be able to analyze and classify any algorithm in a way that is rigorous, consistent, and meaningful to all computer scientists. Since we are concerned with algorithms, that is the software, we want a methodology that is independent of any particular operating system or hardware. The runtime performance of computer algorithms varies widely. Some algorithms are fast, some are slow, some are very slow. It is important at the onset of this discussion to call your attention to a very important point. The amount of time it takes a computer to produce a solution for a particular problem is irrelevant. That is, we can't determine whether or not an algorithm might be considered fast or slow based on how long it takes a particular instance of that problem to run. Rather, we are concerned with how the amount of time required to run changes as the problem size increases. When we say an algorithm is fast or that it's slow, what do we mean? What are we measuring? Complexity analysis provides the framework. It is the language all computer scientists understand and use. In many areas, we use some type of benchmark or metric for characterizing performance. If we say that a particular car is fast or slow, what does this mean? In fact, these terms are too imprecise to convey any useful information. If a car can go from 0 to 60 miles per hour in less than 4 seconds, you don't even need to say the car is fast. Everyone familiar with cars understands immediately the implications of accelerating from 0 to 60 in less than 4 seconds. Similarly, if a car takes 20 seconds to accelerate from 0 to 60, everyone would agree that that car is slow. Thus, the 0 to 60 miles per hour acceleration time is a commonly accepted metric of performance by people interested in automobiles. This isn't the only metric that might be used. There are many methods we might use to gauge performance. An alternative metric might be horsepower. Suppose we say that a certain vehicle has 250 horsepower. Is that vehicle fast or slow? Does the 250 horsepower number give us precise information about the performance of the vehicle? Not really. If the vehicle is a small, lightweight two-seat car, then 250 horsepower likely means a fast, powerful car. But if the vehicle is a 6,000-pound Bentley, it would be considered slow and underpowered. Thus, although many different ways to measure performance exist, a measurement widely known and accepted is the acceleration time from 0 to 60 miles per hour. It's a better predictor because it expresses performance without regard to size and weight of a given vehicle. It's a better performance measurement tool. Similar metrics exist in many different arenas. Printers are often rated by the number of pages per minute that they can print. Runners can be classified by how long it takes them to run 1 mile. Aircraft are rated as fast or slow based on how close their cruising speed is to the speed of sound, that is the Mach number. So we need a useful metric for characterizing computer algorithms. That metric is the rate of growth. We classify algorithms based on the change in the number of instructions that are executed as the size of the problem increases. That is, consider sorting an array. How many instructions are executed if the array is a certain size? Compare this with the number of instructions that are executed if the array is twice as large. We can also measure the rate of growth in terms of elapsed time. That is, we can either count the number of instructions an algorithm executes, or we can count the amount of time the algorithm takes to run. Both methods give the same result. The change indicates the rate of growth. So in different areas, in different arenas, different metrics are used. We might use the acceleration rate for a car, but when we're talking about algorithms, what we're interested in is the change in the number of instructions required as the size of the problem increases. It might seem obvious and intuitive that if you double the size of the problem, then the algorithm will take twice as long. That is, if it takes 5 minutes to sort an array of size 1 million, then it should take 10 minutes to sort an array of size 2 million. Sometimes this is true, but very often it's not. In fact, if it takes 5 minutes to sort 1 million elements, it more likely takes 20 minutes to sort 2 million. For many sorting algorithms, doubling the size of the array means that it will not take twice as long, but in fact will take 4 times as long to sort. Thus, the idea that doing twice as much should take twice as long does not hold when discussing computer algorithms. Some algorithms do in fact have this linear behavior. By linear, what we mean is doing twice as much takes twice as long. However, many more algorithms have different behaviors. Thus, again, a key concept here is the rate of growth of algorithms. That is, we want to be able to predict how an algorithm will behave, how long it will take to finish the job as the input size increases. Generally, if a problem is small, the time it takes for an algorithm to complete is so short that it's not really measurable. However, as the problem size increases, we may have a situation where it takes so long for an algorithm to finish that the time becomes unworkable. If a certain program needs to run overnight to provide an answer each morning, but the program takes 100 hours to run rather than the hoped for 8 or 10 hours, then it's not workable. Thus, we want to be able to predict how long an algorithm will take to run as the input size increases. So a second important concept here is the input size, which we generally refer to using the variable n. The variable n represents the size of the problem. The actual definition of input size varies and is dependent on the type of problem. For instance, if we're discussing a sorting algorithm, then the size of the array to be sorted is the input size. The variable n is the number of elements in the array. Similarly, if we are searching an array or a linked list for a specific element, then again n is the number of elements in the array or the list. If we are searching a plain text document for a specific word, then the input size is the number of words in the document. Here is a sample problem. Suppose you're the programmer for a restaurant supply company. The company delivers supplies to restaurants on a daily basis. The company has about 100 customers, and on average, the delivery truck makes about 20 stops per day. That is, the truck leaves the warehouse in the morning, stops at approximately 20 different restaurants to drop off supplies, and then returns back to the warehouse at the end of the day. Your boss asks you to write a program to calculate the best, that is, the shortest route for the truck driver to follow each day. You have a spreadsheet with the distance between all of the stops. So you have about 100 customers, and you have a spreadsheet with the distance between each of the customers. So it's a simple lookup problem. Hopefully this example makes the case for complexity analysis and demonstrates why it is important. This is an example of an intractable problem that cannot be solved with a computer. This fact is counterintuitive. The problem seems fairly straightforward. After all, there are only 20 stops. If we have all the distances between our customers, then it becomes a simple matter of looking up these distances and then picking the shortest route. This problem seems simple, and most people would think it's an ideal application for a computer. A programmer with no formal training in computer science might even try to write such a program, but no computer scientist would ever bother with it. It is the computational complexity of the algorithm that reveals the fact that it is in fact intractable. As you can see on the chart here, if there are 20 stops, the predicted time to run is about 77 years. In particular, notice the rate of growth as the input size or problem size increases. With 10 stops, it takes less than a second. If we double the input size to 20 stops, the time increases from less than a second to 77 years. This demonstrates in a rather dramatic way the fact that doubling the input size does not always result in a doubling of the time needed to run. We say that this algorithm is intractable because the computer will probably crash or break down long before it finishes. And even if it were able to keep going for 77 years, no one would care about the answer by the time it did finish. Thus, we say this problem cannot be solved by a computer. The reason this algorithm is so bad is because the number of routes to consider is the number of stops factorial. With 20 stops to consider, there are 20 factorial possible routes to evaluate. 20 factorial is, of course, a very, very large number. The runtime of 77 years is based on the program evaluating 1 billion routes per second, which is in fact a very generous estimate. We should note that it is possible to solve a variation of this problem. We can calculate a good but not guaranteed to be optimal route in a reasonable amount of time. A less dramatic but perhaps more relevant example is this comparison between two sorting algorithms. Sorting is something we do frequently, and it takes a great deal of work on the part of the computer. Here, the selection of the sorting algorithm can make a dramatic difference in runtime. When the input size is small, it doesn't really matter which algorithm is used. If you're sorting an array that is never larger than 100 elements, then bubble sort is just as good as quicksort. In fact, it might be preferable because it is simpler. But as the array size increases, the difference between the two algorithms becomes striking. Notice the growth rate for the two algorithms as the size of the array increases, and notice the difference between them. The times are in milliseconds and are actual times measured on a mainstream computer. With an array of size 1 million, bubble sort is expected to take about 1 hour. For the same sized array, quicksort will take about 1/10 of a second. Even though both algorithms do precisely the same thing, they sort an array. One algorithm will take an hour while the other takes 1/10 of a second. It's not always practical or even possible to run timing tests on algorithms. Even when we can, there are problems with this approach. There are other factors that impact the times we observe. First, virtually all modern computers and operating systems are multitasking. On a Windows computer that is idle, somewhere between 40 and 60 processes or programs will be running. Each process consumes some CPU resources. Thus, if we're timing an algorithm, we're actually timing the algorithm plus everything else the computer is doing during the timing test. Also, the architecture of the system will have an impact on timing tests. We may see dramatic spikes in the amount of time required when caches get filled or a read from disk is required. Therefore, we need to have a way of analyzing algorithms to predict in a rigorous and repeatable way without having to do timing tests. There are several key concepts here. First, our analysis should be independent of any particular computer hardware or operating system. Also, we need a metric or a way of characterizing performance that can be understood by all other computer scientists. We need a common language or framework for describing the performance of algorithms. Thus, an analysis done in 1960 should be correct and relevant today. An analysis done today should be correct and relevant in the year 2060. The analysis process starts with the function that describes the work done by the algorithm in terms of input size n. What we want to do is write a function that reflects the amount of work done in terms of this input size. This function shows the rate of growth or the asymptotic complexity of the algorithm. The process for doing it is as follows. First, we look at the computer code and identify the input size. So in the first example here, the number of times hello world prints is determined by n. If n is equal to 10, then the algorithm prints hello world exactly 10 times. If n is equal to 1,000, then the algorithm prints hello world 1,000 times. This should be obvious. Thus, the variable n represents the problem size, and we can write a simple function to describe this as f of n is equal to n, linear. In the second example, we have two loops, one nested inside each other. For each pass of the outer loop, the inner loop runs n times. That is, when I equals 0, the j loop runs n times. When I is equal to 1, the j loop runs n times. When I is equal to 2, the j loop runs n times. Thus, hello world is printed n times n times. We can write the function as f of n equals n squared. The input size is represented by the variable n. The amount of work done by this algorithm is controlled by n. If n is larger or smaller, then the amount of work done is also larger or smaller. For the first algorithm, the rate of growth is n. For the second, the rate of growth is n squared. That is, if we double n, the amount of work done by the first algorithm also doubles. With the second one, when we double the input size, the amount of work done is 4 times as much. Notice that these two code segments have a different rate of growth. The first grows at a linear rate, the second at a quadratic rate. As we can see on the chart here, with f of n equal to n, the single for loop, our first example, hello world prints exactly n times. With f of n equal n squared, hello world prints exactly n squared times. Now we want to consider some common tasks, some operations that programmers have to do all the time. I want to demonstrate the process for examining the code and writing a function to describe the rate of growth. Remember that our primary concern here is the input size. Since all of these algorithms operate on an array, the size of the array is the input size. Many algorithms have initializations or assignments to temporary variables. If the number of steps required for these operations remains the same regardless of input size, then we can just ignore them. So our first algorithm here is search for an element in an unordered array. That is, the parameter is an element we want to find. We must search the array and compare the element with that we are given with elements in the array until we either find it or we're certain that it's not in the array. That is, there is a found and a not found condition possible. What does it take? How much work is involved to either find the element we're looking for or know for certain that it's not in the array? And how does the amount of work change as the input size increases? First, we want to determine the input size n. Again, if we're performing an operation on an array, then the input size n is the number of elements in the array. So array.length is n. In this case, since the array is not in sorted order, we must examine each element in the array until we have either found what we're looking for or run out of places to look. We start at index 0 and check to see if that's what we're looking for. If it is not, we move down to index 1, then index 2, then index 3, and so on until we either find what we're looking for or we run off the end of the array. Thus, in the worst case, we would have exactly n comparisons. In the average case, if the array elements are more or less randomly distributed, we would probably end up examining about half of the elements in the array. Thus, our function is f of n is equal to n in the worst case, and f of n equals n over 2 in the average case. The next algorithm we want to consider is search for an element in an ordered array, and we have binary search in parentheses. A simplistic approach would be to follow the same approach we used with the unordered array. That is, we could start at index 0 and see if that's the element we're looking for. And if it's not, then we move down to index 1 and keep going. So we would start at the beginning and work our way down the array until we either find the element we're looking for or pass the point where it would be. Since the array is ordered, once we pass the point where the element would be, if it were in the array, we can stop looking. If we take this approach, our function is f of n equals n. That is, we potentially look at every single array element in the worst case. But can we do any better? Well, we can. We can take advantage of the fact that the array is in sorted order. We can use binary search, which is far more efficient. It has much better complexity, as we shall see. Our look at binary search here is quick and cursory. However, this is such an important algorithm, we will be taking a much deeper look at it in a future lecture. The basic idea of binary search is this. We go to the middle of the array and check to see if the middle of the array has the element we're looking for. If it does, we're done. But if it does not, then we know something. At the middle of the array, we check and compare that with the element we're looking for. And we can tell which way to go, either to the left or the right. We know this because the array is in order. So I want to take a little closer look at this, so I'm going to switch to the sketch pad and we can take a look at how this actually works. Alright, just for the sake of arguments, let's assume that the element we're looking for is 750. The element to find, 750. Alright, now we have an array here. And just for the sake of argument, let's say that this array has 100 elements. Okay, so with binary search, we go directly to the middle of the array. And we look at the element we find there. So let's assume that we have gone to this array and the element here we have found is 125. Okay, this gives us some useful information. We're looking for 750. Is it possible that the 750 is over in this section of the array? Can it be here? No, of course not, because the array is in sorted order. If there is a 750 in the array, then it must be over here. It must be to the right of the 125. What that means then is that we can discard this section of the array without even looking at any of the elements in it. We don't have to do any comparisons at all. So we have essentially cut the size of the array in half. We have done one comparison and cut the size of the array in half. So we now have 50 elements. Again, we go to the middle of the array and look at what we find there. So suppose we go here and we find 400. Again, the fact that the array is ordered gives us information. If there is a 750 in the array, it must be on this side. It cannot be on this part, so we can discard half the remaining elements. So now we have another section of the array to search, half the size of the preceding one. It has 25 elements in it. Alright, so we do this again. So we keep cutting it in half each time until we either find what we're looking for or discover that it's not in the array. 12 elements, 6, 3, 1, and then finally there's no place left to look. It turns out that this cutting in half is an important concept. This is logarithmic behavior. So if we have an element with 100 elements, then 2 to what power is equal to 100? Well, 2 to the 6th is 64. 2 to the 7th is 128. So 2 to the 100, or 2 to the 6th is the floor, 2 to the 7th the ceiling, with 100 elements. So how many comparisons do we have? We have about 8 comparisons here in the not found condition. So we have log base 2 of n plus 1 steps. This is our function. F of n is equal to log base 2 of n plus 1 steps required. It's the cutting in half that makes this efficient. Okay, the next algorithm we want to consider: find the smallest element in an ordered array. Well, this is easy. Since the array is in order, finding the smallest element is trivial. It must either be the first or the last element in the array, depending on whether the array is in order, is in ascending or descending order. It must either be the first or the last element. Moreover, in this case, there's no concept of input size. It will require exactly the same number of steps whether the array has 10 elements or 10 million elements. Thus, we have the function f of n equals c, where c is some constant value. Our next algorithm is find the smallest element in an unordered array. In this case, we need to find the very smallest element in the array, but the array is not in order. It follows then that we have to look at every single array element to be certain we've found the smallest one. That is, with preceding algorithms, we've been able to stop partway through. When we're searching for a specific element, once we find it, we can stop. But in this case, we're asked to find the smallest element in the list, or the array. If we fail to check every single element in the array, then we may end up missing the smallest one. Therefore, we must do exactly n steps. Our next algorithm is look up an array element given the index. Again, this is a simplistic process. We're given the index of the array element we want. In this case, we don't have to do any comparisons or actually look for anything. We just return the element at the given index. Moreover, there's no concept of input size in this case. The amount of work required is the same whether the array has 10 or 10 million elements. Thus, our function is f of n is equal to some constant c. Here are some common functions that we see all the time. It turns out that there is a fairly small number of functions that we're going to be working with. This chart shows the most common ones with an example of the algorithms that correspond to that function. So, complexity function C that we've just talked about, this is constant time. Examples of this is find the min or the max element in an ordered array. Look up an array element given the index. We have login, which is binary search. With binary search and login performance, when you double the input size, you increase the number of comparisons by 1. They don't double at all. Therefore, the growth rate for all logs is very slow. In, linear, do something with everything in an array. For example, print it. In log in. The fastest sort algorithms are in log in, and quicksort is a good example of this. In squared. The primitive or simple sorting algorithms tend to be in squared algorithms, and this is much, much worse than in log in. In cubed is matrix multiplication, and then past that are the types of algorithms that you typically will not cover in CS 310. there's quite a large group of algorithms that are very, very slow. The complexity of them is dreadful. You will study those in a later course. All right, so we have spent some time talking about finding a function that describes the rate of growth of our candidate algorithms. Now we want to talk about bounding symbols. There are 5 bounding symbols pictured here. Big O, little o, theta, big omega, little omega. What do these symbols mean? Big O is a complexity class. It is a set of functions. And so when we identify our candidate with a complexity class, we will use one of these bounding symbols. If a certain function is big O of n, that means that the function grows at a rate less than or equal to n. In other words, big O of n is the set of all functions that grow at a rate equal to n or more slowly than n. Functions that are classified as little o are strictly faster than, grow more slowly than n. Theta, they are equal. Big omega, greater than or equal. And then little omega, strictly greater than. So I want to switch again to the sketch pad and look at this for a moment. We have big O of n. All right, this is a set of functions. So we want to do a little graph here. This is n. Big O of n is the set of functions on or below the line. It is all the functions that grow at a rate equal to or more slowly than n. So it is this set of functions here. So, is it true that log of n is equal big O of n? Is that true? Yes, because the log function grows much more slowly, and it is in the shaded area. Therefore, it is a member of the set of functions that grow at a rate equal to or more slowly than n. Big O of n. All right. Little o of n. And these are algorithms that grow more slowly than n. These are strictly better than n. So for instance, n equals little o of n. Is this true or is it false? Again, we're going to draw a graph. This is n. Note, however, that little o does not include the line. So I'm going to go ahead and modify our line here and take out sections of it, make it a dotted line. The line is not included. So the region representing the set of classes that are little o of n, we're now shading everything that is strictly faster. That is, the algorithm is faster in the sense that it grows more slowly than n. Therefore, this is false. N is not better than n. However, log base 2 of n is equal to little o of n. What about our constant c equals little o of n? What does that look like? This is some constant number here. Not a very good straight line. Yes, it's in the shaded region. True. True. These functions, log base 2 of n, some constant c, grow at a rate strictly better than n. Right. The next one, theta. of n. This is the set of functions that grow at a rate exactly equal to n. There is no shaded region here. It is exactly n. So can I say that log base 2 of n equals theta of n? No, we cannot. This is false, because log base 2 of n does not grow at precisely the same rate as n. This is not true. N equals theta of n. This is true. It does grow at precisely the same rate. So theta means it grows at precisely the same rate. It's a tighter bound. Our next symbol is big omega. Big omega of n is bound from the other direction. Big omega of n means the set of functions on or above the line. This is the set of functions that grow at a rate equal to n or faster than n. These are algorithms that are worse than or equal to n, greater than or equal the growth rate. So the shaded section here represents the set of functions in the complexity class big omega of n. So some examples. Log base 2 of n equals big omega of n. True or false? No, this is false. If we graph log n, it's down here. It is not in the shaded region. This is false. N equals big omega of n. Is this true? Yes. Yes, it's true. It grows at a rate equal to n. Therefore, it is in the complexity class big omega of n. What about n squared? True or false? Again, this is true. If we graph n squared, we see that it is in the shaded region. It grows at a rate faster than n. So yes, this is true. The last symbol we want to examine is little omega of n. Little omega of n is also bounded from above, but this again does not include the line. It is the set of functions that grow at a rate strictly faster than n. Not much of an artist here. All right, n equals little omega of n. Is this true or false? No, this is false. This is false because it is not strictly worse than, does not grow at a rate faster than n. This is false. N squared equals little omega of n. This is true. N squared grows at a rate strictly faster than n. It is in our shaded region here. N cubed, same story. Yes, this is true. N log n equals little omega of n. Yes, also true. N log n grows at a rate strictly worse than, strictly faster than n. Just a side comment here. Sometimes I encounter a student that believes that n log n grows more slowly than n, that it is less than n. I suppose the thinking goes that a log n is a fraction, and therefore a fraction times n must reduce n, but that's not really the case. N log n is in between linear and n squared. Linear, n squared, and n log n is somewhere in the middle here. So n log n is worse than linear, but not as bad as n squared. Here's the formal definition for these complexity classes. Big O of G is a set of functions f such that for some constant c greater than 0 and some n sub 0 f of n is less than or equal to c g of n for all n greater than n sub 0. Now it's important that you understand the formal definition, but what's even more important and what's really critical is that you understand what the complexities are and how they work. You need an intuitive understanding of what the complexity classes represents. A couple of comments are in order here. First, the c, some constant c times g of n, and also a comment about the n sub 0. I'm going to defer discussion of the c for a few moments. We're going to talk about coefficients, lower order terms. We're going to discuss those in a minute, but for now I want to talk about the n sub 0. All right. So if we have a graph here, and suppose I graph n squared, it might look something like this. Now suppose I graph log n, and it might look something like this. Log of n. We're not specifying the base. Notice, if we're very close to the origin here, that it appears that log n is greater than n squared. This area here does not accurately reflect the trend. Well, what we really are looking at, what we care about, is what happens with these functions as n goes to infinity. As n gets large, what happens? The n sub 0 is the point where you get far enough away from the origin that the behavior from this point to infinity does not change. That is, from this point to infinity, n squared continues to grow at a faster rate than log n. N squared is greater than log n. So n sub 0 is this point where the behavior from that point to infinity is consistent. If you look at points close to the origin, you may get the wrong result. Therefore, we have the n sub 0 to ensure that you're far enough away from the origin to ensure consistency. There are two general ways of determining whether or not a function fits into a given complexity class. So one method is to find values for the c and the n sub 0 that are given here in the formal definition. The other way is to take the limit of the ratio. I find using limits the easiest way to do it, so that's the method that we will be focusing on. The best way, again, to determine set membership in one of these complexity classes, that is big O, little o, theta, big omega, little omega. We take the limit of the ratio, function number 1 over function number 2. The limit as the input size n goes to infinity. If the result of this limit is 0, then that means the denominator grows at a faster rate. G grows at a faster rate than f. If we end up with a constant that's not 0, then they grow at the same rate. However, if we end up with infinity, this indicates that f grows more quickly at a faster rate than g. So what you want to do when it's in doubt is to go ahead and use limits to determine whether or not it is a member. Your candidate function is a member of the given complexity class. So we've got some examples here that we want to look at. True or false? N is equal to big O of n. Okay, so what we want to do is to go ahead and take the limit. The limit as n goes to infinity of n over n squared is equal to, this limit is equal to 0. It should be obvious that n squared grows at a faster rate. So our limit here is 0. This tells us that n squared grows at a faster rate than n. Simple and obvious. Our next problem. N equals big omega of n. This is true. If we take the limit, we're going to get a number or a constant 1, the limit of n over n. So again, as you can see, these are obvious and easy. The one that grows at the faster rate can be determined by taking the limits. Some refinements here. An algorithm not dependent on input size is big O of 1 or theta of 1. That is, by convention, where we had f of n equals c, those functions are in big O of 1 or theta of 1. Big O of 1 is more common, but theta of 1 is also correct. This does not mean that exactly one step happens or one instruction is executed. Rather, it means that it's a constant amount. Input size must be a positive integer greater than 0. We cannot have a problem in the negative range. That is, the input size can't be negative and it can't be 0. The problem must exist. Functions that are used to describe the amount of work done by an algorithm where there is an input size are strictly increasing functions. What that means is a larger instance of the problem can take the same amount of time, or it can take more time, but it can't take less time. Discard constants, coefficients, and lower order terms. This is a case where doing complexity analysis becomes easier. There are not too many instances in math classes where you get to throw away constants, coefficients, and lower order terms. But when we're doing complexity analysis, that's what we do. It makes life easier. All logs grow at the same rate regardless of the base. So log base 10 and log base 2 will grow at the same rate. All exponential algorithms grow at a rate faster than any polynomial bounded algorithm. When we say exponential algorithm, we mean that there is an n in the exponent. With a polynomial bounded, the n is not in the exponent. So c to the 2n power is an exponential algorithm. 2n squared is a polynomial algorithm. Factorial algorithms grow at a faster rate than exponential functions. And then some basic properties here. Big O of f plus big O of g is equal to the max big O of f plus big O of g. This means big O of n plus big O of n squared is equal to big O of n squared. However, it's different with multiplication. Big O of f times big O of g is equal to big O of f times g. So big O of n times big O of n squared is equal to big O of n cubed. If f is equal to big O of g and g is equal to big O of h, then f is equal to big O of h. F is equal to big O of g if and only if g is equal to big omega of f. That is, they have the line in common. If f is equal to theta of g, then g is equal to theta of f. Consider the simple function f of n is equal to 4n. We have asserted that 4n is in theta of n. What this means is that the function f of n equal 4n is a member of the set of functions that grows at a rate identically equal to n. That is, they grow at a rate exactly the same. This is a critically important point that you need to understand. As we look at the graph of n and 4n, they do not appear to be equal. In fact, the gap between the two increases as n increases. When the input size n is fairly small, the lines representing n and 4n are close together. But as n increases, they grow further and further apart. Yet in terms of complexity, they are equal. Not only equal, but identically equal. This might seem like a contradiction. It's certainly not true that n is equal to 4n, unless, of course, n is equal to 0. But the important point, n and 4n grow at the same rate. So what we mean when we say that they're equal is that they grow at the same rate. If we take the limit of n over 4n, we can see this. Is it true that 4n is equal to theta of n? The way to find out is to take the ratio of the functions. 4n over n, taking the limit as n goes to infinity. And this is an easy one. That limit is 4. It is a constant not equal to 0. Therefore, 4n is in big O of n. True. n and 4n grow at precisely the same rate. So here is another way to look at the same issue. In this simple chart, we have f of n equals n and f of n equals 4n. Each row is double the value above it. That is, n goes 2, 4, 8, 16, 32. For the column with f of n equals n, we see an exact doubling of the row above. The first row is 2, and then we go to 4, and then to 8, to 16, to 32, to 64. But notice what happens with the row f of n equals 4n. We start with 8. And then the row below, we go to 16, then 32, then 64, then 128 and 256. In other words, these two functions grow at the same rate. Every time you double n, 4n doubles as well. So when we double n, the number of steps it takes is also doubled. So these two functions grow at precisely the same rate. For that same reason, we're able to discard lower order terms and constants. That is, the limit as n goes to infinity is shown here. We have the function 2n cubed plus 25n squared plus 50n plus 100 is equal to theta n cubed. In other words, the assertion is that this function grows at exactly the same rate as n cubed. And when you take the limit as n goes to infinity, you end up with 1/2, a constant that's not 0. Therefore, these two functions grow at precisely the same rate. Of course, n cubed is not equal to this function. When we use the equal sign, what we're doing is we're indicating set membership. That is, 2n cubed plus 25n squared plus 50n plus 100 is in the set of classes that grow at a rate n cubed. All logs grow at the same rate regardless of the base. We know that log base 10 of n and log base 2 of n grow at the same rate if the limit of the ratio is equal to some constant. Well, this we can prove. We can start with an identity. Log base 2 of n is the natural log of n over the natural log of 2. So we can take a ratio of these using the identities, and when we do this, we discover that we end up with 3.32, which is a constant not equal to 0. Thus, all logarithms grow at the same rate. This is useful because you may substitute if it simplifies the evaluation. That is, there are times when it's easier to evaluate one log rather than another. In many cases, L'Hopital's rule also is useful. because you can take the derivative of the ratio rather than just the ratio. An example of where this is useful, suppose our function is n to the 3/2. Well, is n to the 3/2 in the complexity class big O of n log n? Recall we said that n log n is between n and n squared. N to the 3/2 n to the 1.5 is also in between n and n squared. But does n to the 3/2 grow at a rate greater than, less than, or equal to n log n? So again, what you must do is take the limit to see if this is true or false. So first we have a simplification, and then we take the derivatives. We take the derivatives and we see then that we get infinity. When we have the result of infinity, that tells us that n to the 3/2 grows at a rate faster than n log n. Therefore, n to the 3/2 is not in the set of functions big O of n log n. All polynomial algorithms are slower than exponential algorithms. So we have an example here of an exponential algorithm, and you can see the n and the exponent. So this is a very small exponent, 0.000, a number of zeros in the 1 n equal to big O of n to a very, very large polynomial. But when we take the limit to evaluate this, the exponential algorithm wins. Therefore, exponential algorithms grow faster than any polynomial bounded algorithm. So a recap of the essential points here. Input size is always a positive integer greater than 0. You can't have a negative or a non-existing input size. Functions used to describe the amount of work done by algorithms where there is an input size are strictly increasing functions. That is, you cannot increase the input size and do less work. When doing an analysis, discard constants, coefficients, and lower order terms. The reality is that the higher order term totally dominates. Lower order terms, coefficients, and constants have no impact at all on the growth rate as n goes to infinity. All logs grow at the same rate regardless of the base. Therefore, you can feel free to substitute one log for another if it makes the evaluation easier. All exponential algorithms grow at a rate faster than any polynomial bounded algorithm. Factorial functions grow at a rate faster than exponential functions. And then finally, the properties we discussed here, big O of f plus big O of g is equal to max fg. Big O of n plus big O of n squared is equal to big O of n squared. Big O of f times big O of g, however, is different. It is big O of f times g. So big O of n times big O of n squared is equal to big O of n cubed. If f is equal to big O of g and g is equal to big O of h, then f is equal to big O of h. If f equals big O of g, then g has to equal big omega of f. If f equals theta of g, then g equals theta of f. Finally, remember that the equal sign here denotes set membership. When we say f is equal to big O of n, we are saying that f is in the set of functions big O of n. Finally, we need to mention that although complexity analysis is extremely useful and important, it does have a weakness. The coefficient or lower order term may be large enough that the analysis will hold true only for very large input sizes beyond what we would normally see. As an example, a well-known sorting algorithm requires 64n steps. I'm referring to radix sort. Well, 64n is equal to big O of n. Yet if we time this algorithm For array sizes that will fit in memory, this algorithm is slower than quicksort, which is in fact a big O of n log n algorithm. The analysis says that radix sort is faster, but in fact it's noticeably slower when we run actual timing tests. That doesn't mean that the complexity analysis is not valid, only we must be aware of its weakness. Algorithm analysis is not a topic that we'll cover briefly in 310 and not revisit. In some of your classes, you may cover a topic and then move on to something else, never returning to that topic again. But that's not the case here. Rather, we will be analyzing and discussing the complexity of all the algorithms covered in this class. This is an essential tool for all computer scientists and one you must master. In our next lecture, we will be doing a number of examples in an effort to help you do just that.